put your email and receive the Zoom link. Hopefully, see you there. And it's an interesting topic, as Mr. Hagigat was saying. So,
because the reason, because we are working with a company here in Montreal, and they are producing some software trying to analyze this data, because as I mentioned, you have 6,000, 7,000 points. If you look at how bigger building is more. Now the question here, how fast we can analyze and make sure this data makes sense. And we have a project with this company, and there are 4 of our graduate PhD students working with this company and trying to develop a sort of software. They can analyze it, make the decision, and send the signal back and so on, because 5 or 6 point is easy, but when you're talking 7,000 points in government office, that they have measurement at every point, at every room, every thermostat, every compressor, every pump, and so on, is a very huge task how to analyze it. We try to see if we can get this gentleman, the owner of this building, and give a presentation to you guys one more time, once in the future. Anyway, let's go back to reality. The reality comes back to our presentation. We mentioned that, let me share my slide. Now I have a problem with the system we have, because we have only one monitor here, and my monitor is not working, the other one. Can you see my slide, please?
yes.
Okay, let me get rid of this name here, because my slide here, okay. As I mentioned, now we are also looking about the time, because so far we are looking about the temperature distribution on the body, inside the body, but only at a steady state scenario. But how we look at the temperature distribution as a function of time. As a simple, if you look at the wall outside, when it's sunny, there is a sunshine, there's a lot of energy comes from the sun, it's absorbed on the surface of the wall, but all of them directly, immediately will not enter the room. It comes as a function of time. As I mentioned, we can now discretize any wall, any body system that you would like to analyze it. And the question, we're trying to find the answer only to those points. The differential equation was giving you distribution, the answer throughout the wall thickness. But when using a numerical, it provides us at a specific point that we write the energy balance for that equation. And for example, we select the slice of the wall here, and the distance between this point and this point, delta x, and here is delta x. Therefore, the thickness of this control volume is delta x, because it's half of this and half of that. And we wrote the energy balance. We mentioned conduction comes from m-1, conduction comes from m+1, plus the amount of energy generated inside this thickness is equal to the change of energy, the temperature of that control volume as a function of time. And time is represented with this notation of I and I+1. Therefore, shows that variation of the temperature of node M at 2 time step, now and a future time step. Again, this represents the time step. It means the time step could be 5 minutes, could be 1 hour, could be 10 hours, depend on the way we are solving the problem. Now, the question here, these are specify the time, but how about this side? And we mentioned there are 2 techniques, explicit technique, that we always look at the present time, trying to find the temperature at the future time. Therefore, if I summarize this equation here, end up here is, I want to calculate the temperature at node number M at the next time step as a function of the time temperature at the previous time. Or I can write this equation in the form of implicit one. Therefore, all of them, I will write it for the future. I know the temperature now, I'm trying to calculate the temperature in the future. The equation becomes in this format. Therefore, I know the temperature now, I'm trying to calculate the temperature in the future. The next time step, next time step, and so on. Therefore, these were the 2 techniques that we discussed. Now, if I go back to the problem that we are trying to do, I'm going to spend some time to show you how to solve this problem. Again, it's the same thing that we had before. We have a room. Again, this room is the temperature we have here. We're trying to calculate the temperature. As you may notice, if you take last course outline, I send it to you. You do not need to calculate the load. The only thing I need to calculate the temperature. Therefore, please look at the course outline number. The last one I sent it to you, and that's asking the same as project number 1. Try to calculate the temperature distribution. Therefore, now remember you have a thick wall, I believe it was around 40 centimeter. Therefore, the solar radiation comes here will not immediately affect the temperature inside the room. If you look at the result of your project number 1, you will see as the temperature increases here, the temperature in the wall increases immediately. But in reality, there are a lot of mass here. And some of the solar radiation will affect to change the temperature of this part, and portion will go through here and so on. Therefore, probably takes some time. We call it time lag, as you notice in the example we did in chapter 2 and 3, 3 and 4. It takes time lag that some of this energy comes through here, okay? Therefore, it's not immediate, it takes some time. Therefore, how we're going to solve the same as we did it before. We discretize this wall to a number of the point, 3, 4, 5, as you wish, okay? For example, if I look at the west here, the west wall here, my temperature distribution becomes like this, exactly the way we did it last time. Therefore, this is represent the temperature of the wall exterior surface. This is one point inside, this is another point, and this is another point, and here is the temperature inside the room. Therefore, I discretize it to the 3 part areas. 1, 2, and 3. You can do it 4, 5, 6, whatever you would like. Again, here I assume all the wall has the same physical property, the thickness, K, conductivity. You can have different value, it doesn't matter, as long as when you write the equation, you keep track of the thickness and thermal conductivity, specific heat, and so on. Therefore, if I write the equation for node number 1 here, as exactly we did last time, we have some solar radiation comes in the exterior surface of the wall. You can multiply by alpha, I forgot, alpha, the absorptivity of the wall. And then you have convective heat transfer to outside. Therefore, this represents convective heat transfer to outside. And that's equal H TO minus C1. Again, as I mentioned, we write summation to that point, okay? The energy go to point number 1. And also we have some conduction is coming from T2 to T1, and that's represent conduction. Therefore, this is exactly the part that you had it in project number 1. But is equal now the variation in the temperature of the node 1, okay? Therefore, here is mass of node 1, okay? Again, divided by A because I wrote it per unit area, okay? This A could be multiplied by them, doesn't matter, okay? Times Cp, therefore mass times a specific heat of the material that we have. And here is a variation of the temperature node 1 as a function of the time, now and future. Therefore, there is some variation in the temperature. It could be increasing or decreasing. What period of the time is delta T? Therefore, this is joule here. This is joule per unit of time. Second is exactly the same as this one. The same thing I can write for temperature number 2, node number 2. For node number 2, I'm writing conduction come from this point. Conduction come from this point. Look at here, it's conduction from T1 to T2. Conduction from T3 to T2. Please keep right, always right to the point. Change of the mass of slice number 2 here. Number 2, point number 2 here. It has a certain mass divided by area. Again, the same as variation of the temperature now and future. I put T, just keep in mind, in your textbook probably they put I, but I put a specific heat that keep in mind this is a time variation, okay?
Sir?
Yes, sir.
So M1 and M2 represent the mass of
node number 1 and node number 2.
Okay, so the for M2, for example, it's the mass of the wall between T3 and T1.
I will go to next slide. I will good point. I just wait. I will go to next slide. I will show it to you. Okay. Therefore, here it's representing here. The same thing I will write for node number 3. Again, node number 3, conduction from T2 to T3, conduction from T4 to T3. That's exactly here. Conduction, conduction. And since this is interior node, therefore there is not no other sources. Remember, our wall, we don't generate any heat. Okay, there's no heat generation. And here represent variation of mass number 3 here, the layer here 3, we specify later on. And here is that variation. And the same thing for node number 4, okay? Therefore, we can write all of this equation and now as partial time. The only thing you have to keep in mind that T1 is a boundary. Here we are talking about the wall, here representing the air, okay? Therefore, here we have to make sure. And T number 4, again, this is interior surface of the wall that we have, and here is the interior temperature, okay? Therefore, here, this is solid wall, we call it, and equation 2 and 3 are almost the same, but here we have a convective heat transfer to inside and convective heat transfer to outside, plus solar radiation. Let's go back to the question was asked, okay? And let me go to this next slide, then if you need, I can come back here. Look at here is T1. This is T2, and I just draw T3. I didn't draw the rest, okay? As I mentioned here, we have to specify that T1, the node number 1, which part is representing, okay? Therefore, we divide the surface area here between these two here that we have, okay? Therefore, here is node number 1, T, and here T2. And the distance between them is delta X. Therefore, we draw a boundary here according to United Nations, okay? And we mentioned this is the boundary between node number 1 and node number 2. Therefore, this half belong to here and half belong to here. Again, the distance between T2 and T3 is delta X. I divided equally here. I mentioned this part belong to 2 and this part belong to T3. Therefore, if you look at here, the mass representing T number 1, node number 1, is this part, delta X over 2. The distance between this point and this point is delta X over 2. And the mass representing to node number 2 here, delta X over 2 here, delta X over 2 here. Therefore, from here to here is delta X. Therefore, keep track of the mass when you're writing equation, okay? Therefore, if I write it for here, this represents mass of node number 1, okay? And therefore, here is, I can write it down. M divided by A, because I can, like as I mentioned, I wrote it here, is delta X. Delta X times A become the volume times the density, but remember, is only half of this space belongs to node number 1. If you would like to visualize it, look at here is, this is representing node number 2. Node number 2, this mass represents node number 2. Half from here, half from here. Therefore, this becomes M over 2 here. Any question here?
Materials.
Yes, sir.
So in case that the right hand is material and the left hand is other material.
Then if
and
you have,
it's okay.
That's okay. Very good question, sir. If it's the case here, assume this is one material and here is another material, right? Let's assume this part representing representing a material A and B, right? Therefore, when you consider this part represent material A, you consider the density of A, and this side you consider the density of the B and the specific height of the B. Therefore, this term become, for example, for node number 2, become delta X over 2 times rho A plus delta X over 2 times rho B. Did I answer your question, sir?
Yes, thank you.
No problem, sir. Therefore, exactly, fantastic, because I believe your wall again is made of two material, mud and stone. Therefore, if this is exactly intersection of two wall, and mud and stone, therefore this part belong to one material and this part belong to material. Therefore, this become by itself become two different color. Okay, this is one material, this is another material. Very good question, sir.
What's the
M?
M1, M2?
What's the M1, M2? Okay, let's go back, sir. As I mentioned here, is M represent the mass of node number 1. Because this, we are trying to find out how much energy has been stored or released from node number 1. Because this is representing a mass. Therefore, if you have solar radiation at, let's say in the morning, let's look at 10 o'clock in the morning, from the west wall, there is a lot of solar radiation come is your west wall. Therefore, the temperature goes up and it slowly diffuses material. Therefore, here is how much is this material, is the mass of this material. Therefore, that's the term comes here.
Okay, would you say M1 is the mass of the outer surface of the wall?
As I mentioned here, sir, the M1 is the mass of this layer of the wall, not the whole wall, okay?
Okay.
When we discretize, when you select the number here is, let's say, delta X, node number 1 in the exterior surface of the wall, node number 2 somewhere inside, let's say 10 centimeter, and here is 20 centimeter. Therefore, the distance from this node to this node is 10 centimeter, and from here to here is 10 centimeter. Therefore, we have to specify which part of the material represent by 2, which part of the material represent 1. Therefore, we draw a line here, and we mentioned this, the boundary between node number 1 and node number 2. Okay, this is the boundary. This part, again, this is the limitation of when we are using finite difference. If you are using differential equation, we can find the temperature at any point. But here we can only find the solution to node number 1 at node number 2. But we do not know what is the temperature at this point. Therefore, we add this material. We said this part of the mass here represent node number 2. Okay, we assume here this portion, the temperature here and the temperature here is the same. Both the temperature here is the same. Therefore, the whole layer here, this thickness of delta X, are represented by one temperature, and then this part represented by another temperature. Okay, that's when we are changing a differential equation with finite difference. Therefore, we can calculate the temperature at node number 1 at node number 2. We cannot calculate it here. We can break it down to a smaller layer, but that takes more time to do.
Sir?
Yes, sir.
So like you said, if there's two different materials, we use the rho for each of them.
Yeah.
Same thing for outer surfaces, I'm assuming. For, let's say T3 is our inner wall surface. We take the mass.
Let me explain to you again. Look, sir. Okay, look at here.
Oh, I understood that.
Assume here is material A, material B.
I get it, but it's only for the air as well. Doesn't matter. We do the same thing.
For the air, again, good question, sir. For the air, we assume the mass of the air here.
Yes, that's what I'm saying.
Compared to here is much lower. Okay.
Yeah.
So we can ignore it. Okay.
Okay.
We can ignore the mass of the air here. Okay.
All right. Perfect.
That's the assumption here. The assumption here is that the temperature of the air from here all the way to here is the same. We assume the air is completely mixed. Good question, sir.
All right. Thank you.
Therefore, now, Mike, if I use implicit technique, again, implicit technique, the equation that I had will end up this format. Implicit, gentlemen, ladies and gentlemen. Therefore, I have to use the information in the future, the temperature, the solar radiation the next hour, the outdoor temperature next hour to calculate temperature node 1 and node 2, okay? Therefore, the equation that we had before, if I write it implicit, therefore this equation, all of them are at the future time. And I know the temperature here, I'm trying to calculate this for. Therefore, your equation number 1 now, it has been transferred to this format. Again, is radiation comes from the sun, convective heat transfer, again here node 0, node number 1, conduction from 2 to 1, here is from here to here, and energy accumulated in this mass of the wall. And the dimension is delta x over 2, y is over 2, is simply because this layer only represents node number 1. Okay, you can take another delta x here, but air has no mass. Just keep in mind, I forgot to put a row here. Okay, there's a row here. And equation number 2 will end up to this format again. Equation number 2 will end up. I'm sorry. If let me just go back. If I summarize this equation, right here, therefore you can see I have a T1 here. I have a T1 here, and I have T1 here. All of them at future time step, okay? Therefore, this become my T1 here. This is conduction from here. This is convection from here. And this is the mass of the air. Therefore, my equation now become exactly the same as before that you had, but one extra term I have here. Again, and please put the row. I forgot to put the row here, and I have the term here. Before you had this term, conduction, convection, conduction here. And now this is, we add this term here because we're considering now the transient. Therefore, we have to also consider the influence of the mass of the material that we have, okay? Therefore, this is your equation, just simply end up to this format. Just again, I forgot to put a row here and a row here, okay? Therefore, now this is the format of implicit equation that you have. A coefficient times T1, a coefficient times T2 is equal. These are the known value. These are the known value. But keep in mind that you calculate radiation, solar radiation the next hours. You calculate the temperature next hours, knowing the temperature of that T1. T1 at this moment. I'm trying to calculate the temperature of T1 and then T2 at the next time steps, okay? If I go to next equation again, the same thing I get for equation number 2. Equation number 2, I had conduction from 1 to 2, conduction from 3 to 2, and here is the mass of node number 2. Delta X, because now is interior point, and so on, okay? If you have 2 layer, you have to consider material A plus material B, okay? Therefore, this term become 2 term, okay? If it's intersection of 2 layer, mud and stone, okay? Therefore, now your equation again, if I summarize that, become here is the conduction for T1, you're talking T2, you have conduction term, because you have 1 term here, you have 1 term here, that's why you have 2K. Now this is influence of the thermal mass we are considering, transient, plus this is representing for node number 3. And now you have on the right hand side a term, because you know the temperature now. We know the temperature now, we are trying to calculate the temperature next time a step that we are trying to do, okay? Therefore you can see now your formula is changed. Now we have to have an extra term, and that extra term representing the thermal mass of the system. Okay?
Sir?
Yes, sir.
You put a parentheses at the end. Is that not necessary?
Yeah, this is my, yes, I have, this is removed. Yes, that's correct, sir.
Okay.
That's correct. Okay. Now let's go back and then let's see what happened here. Therefore now, if you look at here, before you were trying to solve, you were starting from midnight to next day, right? That was, you had a loop. They said that calculate the temperature, time equal 1, time equal 2, time equal 3, all the way to next day, okay? Therefore, now if you do the same thing here, you calculate T1 and this is T2, and you write all the equation that you had, okay? Therefore, if you have 26 equation, this is equation for node number 1, node number 2, node number 3, number 4, number 6, and this is your node number n. Could be 19, could be 26, could be 36, depend the way you did your assignment number 1, okay? Therefore, you were trying to solve this matrix because this is T1, T2, T3, and so on. You have this one, and this was your right-hand side before, but now you have extra term. For node number 2, before you didn't have any right-hand side, but now you have a right-hand side because the temperature and T2, you know the value at this time, okay? Therefore, you write this one to try to solve, okay? Now, but this is a transient, therefore you have to have a number at the, again, I made mistake, please, this is not T plus 1, this is only a T, okay? This make a distinction, okay? This is T, no, this is correct, I'm sorry, this is correct, okay? Therefore, now you have Q and so on. But when you start your program, what is the temperature of T number 1 here, T1 before? We call it the initial value. What is the temperature of 2 at now? We do not know this initial value. And that's one of the problems that you're dealing with, the initial value problem. Before, you did not have any problem because you did not have this one, assignment number 1. You did not have this one, and you did not that one. Therefore, you were able to calculate based on the number of information that you have. But now you have to have some initial value. You have to have a number in order to solve the problem. This way, you can assume any number. You can assume T1 is 6,000, T2 is 100,000, T3 minus 20,000, and so on. Any number you can assume, okay? Because we call it initial value. At the initial value, it means after 3 hours or 4 hours, its effect disappear. Therefore, these are make an assumption. Therefore, give a number to those points at the time you started. Because now when you start, the program knows this value is equal 6,000. This value is around 100,000, and Tn is 500,000, okay? Therefore, these are you have to give to the program, or you can assume 0. It doesn't matter. You can assume any number. These are, we call it initial value, and its impact disappear. Therefore, now, these are the number you do not know. Therefore, you have to write the program as the number of the day also. Therefore, you run the program not only for 1 day as you did it before. You run it for 5 days, 6 days, 5 days, 2 days, 3 days, doesn't matter. And the question here is, how do you know your answer is correct? Okay, therefore you have to somehow be able to calculate, because when you calculate at number 1 at time equal 1, you come all the way to here and you find a value for T plus 1. It means you calculate the temperature at 1 hour. Then you go back, become 2. Therefore now this value that you had here, this value that you had, it was the value at time hour 1. Therefore you have to keep all of them, replace all of the new value in the order. Therefore you end up in a 2-dimensional matrix that has 2 indexes, x, position, and time, T, N, M, okay? Therefore, you have to T, N, you have to put all the new value to the previous hours, and then you go back, okay? Therefore, you have to do this one all the way going back, okay? Because when you calculate all the T plus 1, before you're moving to the next hour, you place them in the old dimension, and then you go back next hour. Therefore, here at the beginning, you assume all of them this value, but after time equal to 2, You have this before go there. You have to take the value that you calculate here for time number 1, place them in the old value, and then you go back, okay? Therefore, this is, you see there is a loop here from 1 day, and you have to repeat it 3 days, 4 days, just I put 5 days to make sure your answer will converge. It means what that means, it means the effect of the initial value will disappear, okay? The initial value. Any question? Any question, please?
Sir, could you go to last slide, please?
This is last slide, sir.
No, the one before this.
Here is last slide, sir.
Okay, I have it. Thanks.
Sure. Okay, please, while this gentleman is writing, just think, if you have any question, ask, please.
So it has to converge within 5%, 10%, or?
Yeah, that's a good point. Therefore, what you do here is converge. The question here is, how do you know converge? Let me go to the next slide when this gentleman finished. You select one temperature, one somewhere in the wall, okay? One of the point, and compare that temperature today, let's say 4 o'clock in the afternoon, and then you go to next day, you compare to temperature of that point at 4 o'clock. And if the difference between them is less than 0.5 degrees, because this accuracy of the thermostat, then you can say, okay, I converge, okay?
Okay.
Finish this slide, sir?
Yes, I have it. Thank you.
No problem. Therefore, I will go again. As I mentioned the last time, you had this one loop because you did not have the red one. Therefore, you did not need to be worried about this one. But now we have the effect of the previous time step. Therefore, you assume some initial value, and the effect of the initial value will disappear after a certain time, for 2 hours, 5 hours, 6 hours, okay? And then, but again, this since you always need to know the value of the temperature at the previous time, after every hour, let's say time number 1, when you get to finish here, you calculate all the temperature at time equal 1. Before you go in time equal 2, you keep them in then as old one. We call it new, we can call it new one, put it at old one. And then we go all here. Then this becomes time equal 2. In order to calculate the temperature at time equal 2, you need to know the temperature at time equal 1. Therefore, you keep them here, that you have their value. And going back to convergence, again, since you have to run it for more than 1 or 2 days to make sure the effect of the initial value is gone. Here, after, let's say, 1 day here, keep the temperature of one of the nodes. Let's say keep number 3, and compare today with then tomorrow. If the temperature node number 3 today and tomorrow is less than 0.5%, then you mentioned that your result is converged and you can stop the simulation, okay? But if you'd like, you can run it for 5 days, doesn't matter, because it takes only 2 seconds to do that, okay? Any question? Therefore, the same thing that you did for project number 1, it follows the same format, but now we are also looking to see how the mass of the wall will affect the temperature distribution in the wall. You will see it in your result. There will be a delay. For example, in the morning, you have a lot of radiation in the east wall, okay? But all the temperature will not pass through the wall immediately. Probably the temperature takes 3 hours, 4 hours to reach its maximum. Not at that time. Probably takes 3 or 4 hours maximum to show the temperature variation, okay? Therefore, you will see your graph will shift a little bit shift, and there's that we call it time lag. Any question?
Excuse me, sir.
Yes, sir.
For the graphs, do you want all 5 days, or you just want like the?
No, the last day, when your result is converged.
Okay, thank you.
Because after 2 days and 3 days, and the result should be the same. because that will converge, and you will see there's no difference between second day, third day, and fourth day. If you see there's a change, then there's something wrong with your program.
Okay, true. Thank you.
Because your solar radiation is the same, the temperature outside is the same, therefore you will not see that much change. But in your case, since we are dealing with only 20 nodes, you will see the program maximum takes in 10 seconds, 20 seconds to run, okay? Therefore, it doesn't matter if you run for 1 day or 5 days. But that's the way we solve it, okay? Anyway, if you have any question, you can ask me, okay? Let's do some problem going back. This is just a review, just because I know you have to start to get slowly ready for the midterm. Let's read this problem and tell me how we're going to do that. Consider a homogeneous spherical piece of radioactive material. I have no idea what that means. Therefore, we are dealing with a spherical coordinate, okay? And the radius of this sphere is let's say 4 centimeters. That generate heat at this rate. Therefore, there's some internal energy generation inside this sphere. 4 times 10 to power 7. This power 7 watt per square meter. Okay, this power. Okay. The heat generated is dissipated to the environment steadily. Okay. Therefore, now it's inside the sphere, heat generated and then is convected to the outside. Okay. The outer surface of the sphere is maintained at uniform temperature of 80 degrees. Therefore, they provide outside an environment that the temperature will remain at 80 degrees. Okay. And the thermal conductivity of the material that the sphere that we have is 15 watt per degree per meter. Okay. Therefore, that's the conductivity. Now, even specify that it is inside the uniform environment, therefore we assume it's one-dimensional, okay? Therefore, it's not a function of the angle, everywhere is the same, okay? We're trying to express a differential equation and boundary equation condition for the heat conduction through the sphere, okay? Okay, read it one more time. Okay. Don't look at the solution, okay? How we are going to solve this problem? Therefore, this is chapter 2. Therefore, we are assuming in a steady state, okay, steady state scenario. And is only we're looking at the conduction. We assume the temperature on the outer surface of the sphere kept constant at 80 degrees. We're trying to develop an equation to find out the temperature distribution within the sphere as a function of position. Okay. Any suggestion? If you have your textbook, just open chapter 2. Look at.
Sir?
Yes, sir.
Do we use second derivative of t over second derivative of r, since we have a radius right now, plus E generated?
Yes.
Is second derivative of T over second derivative of T temperature over second derivative of T time.
But there is a coefficient there. Remember here we're talking about
1 over alpha?
There is no transient, there is no alpha. But here we're talking about a case that is spherical coordinate, therefore the second derivative of the temperature is correct, but there are some also coefficient there.
Okay.
Because the area
isn't it E generated over K?
E generated over K, but the first term, look at here. If you go here, you can see we are talking about this expression here that you had. We mentioned it's not transient. This term is equal 0. There is heat generation here. We assume it's uniform everywhere outside, therefore it's not the function of phi and theta. Therefore, these are the term does not exist, doesn't exist, doesn't exist. But when you're looking about the cylindrical coordinate, the area is changing. Therefore, we cannot take this derivative outside. This is a function of R, okay? Therefore, the area of that control volume will remain in the bracket here, okay? This area remains the same. Therefore, if I simplify this equation here, this term equals 0, this term equals 0, we have heat generation here, and this term equals 0 because it's steady state scenario, okay? Therefore, this will end up equation like this here. Therefore, remember here, when we are dealing with Cartesian coordinate, X and Y remain constant, therefore we can take them out and cancel out. But in case of cylindrical coordinate is R equal to power 1, and spherical coordinate is R equal 2, because this is because talking about surface area, 4 pi R square. Therefore, this R square is a function of R. You cannot take it out, okay? Therefore, this is will remain inside, okay? Now, therefore, your equation end up with this term. Check again, please, and make sure that you really understand. If you have any question, ask me. Yes, sir.
Can you explain again why the other part of the equation we don't?
Here, because it mentioned is uniform.
Okay.
For at every angle around this coordinate here, theta and phi is the same temperature, because it mentioned outside of the sphere is at constant temperature at every point.
So there's it's all 0.
We mentioned uniform. I do not know the temperature. I'm just at this moment we are saying is this is not a function of phi or theta. Okay, therefore it's uniform. Okay, therefore this term does not exist. This term does not exist, and we ignore transient because we mentioned steady state. This is equal 0. Therefore, we have conduction. This term represents conduction in the R direction, and here represent generation. Therefore, equation will simplify to this format, and right here, okay, this one. And we mentioned here is heat generation is constant because they gave the value. Now you have this, if you look at here, is second order differential equations. Why second? Because there is one dr here and one here. Therefore, remember here, my friend, remember, this is derivative of this one times this one. Therefore, you have derivative of this one times this one plus derivative of this one times this one, okay? Hope you remember your mathematics, okay? And you have heat generation here. Now, it mentioned that outside is 80 degree. On that, I mentioned at R equal R0, the temperature is 80 degree. But this needs 2 boundary condition because it's the second order. What is my second boundary condition? Because in order to be able to solve this differential equation, I need 2 boundary condition. The problem mentioned the outer surface of the sphere is maintained at the uniform temperature at 80 degree. Therefore, uniform, it means everywhere. And R equals 0 is 80 degree. But when I solve this differential problem, I get to this differential equation. He's asking me to develop differential equation. I develop, but now I have to define the boundary condition. The boundary condition one at R equal R0, at the surface of the sphere, the temperature is 80 degree. What would be my second boundary condition?
Should we use the center of the sphere using the K that we know?
Okay, what happened at the center?
So the center only the generation, the heat generation.
No, heat generation is everywhere, from R equals 0 to R equal R0.
No, I'm saying that the center is symmetric. So
Excellent.
So
Therefore, center is symmetric. What that means?
So I can ignore both direction and only use the heat generation.
No. No.
Thermal symmetry?
Pardon me?
He said
You cannot-
thermal symmetry.
Thermal symmetry, what that means, mathematically what that means, I have no idea what that means, thermal symmetry. Mathematically, I'm a mathematician. Tell me what is thermal symmetry, what that means, mathematically.
I think that means thermal variation is only function of radius.
Tell me mathematically, my friend.
I think the heat flux is zero.
What, excellent, what that means?
Means that the derivative at L/2 is zero.
That, excellent, therefore the variation of the temperature at R equals 0 is 0. Symmetric, it means at R equals 0 at the center, because it's symmetric. Symmetric, what that means, it means the temperature at 2 millimeters from each side is the same. Therefore, dt over dr is at R equals 0 is 0, okay? Therefore, one boundary condition, you can write it at R equal R0 is 80 degree. That is specified temperature on site. And the second one, it mentioned at the center at R equals 0. At R equals 0, at R equals 0 is symmetric. It means this is equal to 0. Okay? That's exactly the meaning of it. Okay? Therefore, that's now you develop the mathematical problem here, equation, and also the boundary condition that you need. Therefore, please, when you mention thermal symmetry, it means what? It means variation of the temperature at that point is equal to 0. Okay? Therefore, dt or dr at r equals 0 is equal to 0. Okay? That's the meaning. Okay? Any question, please? Any question, please? Okay. Therefore, we answered to the first part of the problem. Therefore, the first part of the problem said express the differential equation and the boundary condition for heat conduction through the sphere. Therefore, now I have a differential equation and I specify the boundary condition. The second part of the problem said obtain a relationship for variation of the temperature in the sphere. Now I know the boundary condition, I want to develop an equation for the temperature as a function of the R. I want to have an expression that if I put R at any point, I can calculate the temperature. And the last part is asking you determine the temperature at the center of the sphere. We mentioned there is no heat transfer at the center, but there is a temperature. What is the temperature value? Okay. I gave you 3 minutes, please, to do it. Okay. Therefore, we want to solve the differential equation to find the temperature as a function of radius, and I want to calculate the temperature at the center at R equal to 0. Okay. Therefore, we got to this part. Okay. We got this part. Please do it, okay? Now you're sitting at home, you have no excuse, you have pen, paper, calculator, everything, okay? Do it. To solve this differential equation, here is, look at it, is equal 0. Therefore, you have the number for here and so on. These are constant number, and therefore we can multiply by r square and start to take the derivative, okay? Take the integral, okay? Therefore, this is your differential equation. This is constant. This is constant. Therefore, now we're trying to take the integral and trying to find the value of theta. Therefore, the first thing you have to do is this. Therefore, your equation become like this, okay? This is R2 here, show up here because this was 1 over R square. This is constant, this is not 0, okay? Now, you take the first integral, this become R squared dt over dr, and this become 1 over third to power 3, okay? Therefore, this become like this. Any problem from here to here, my friend? Any question, please? Okay, therefore that's good. Now, remember, you have a constant here because when you take the derivative, it was 0, therefore there is a constant here. One of the boundary condition, you can put it here and calculate C1. It mentioned at R equals 0, you can calculate this one, okay? Therefore, we can go back and put it here at R equals 0. This was 0. At R equals 0, we mentioned there is no symmetric, this equals 0. You have the value for this one, and you have the value for this one, but here is to power 3, this becomes 0. Therefore, from this boundary condition, we find that your C1 is equal 0, okay? Therefore, this is 1. Now you have this value 0, therefore this is, now you have, again, you can divide by R2, and you can calculate it, take the second derivative, okay? Therefore, now you'll equate, yes, sir.
For the first equation on top, shouldn't the dr be on the other side, the lower dr?
This
the first
one?
Yes.
Why
Shouldn't
should
be on the other side?
No, why should be the other side? Look at here. Look at here.
Integrate both sides.
No, this was here, okay? This is the equation we're talking here.
Yeah.
This is the derivative of this term. This is the derivative of this term. This cannot be multiplied by anything. This represent the derivative of this term, okay? But R is a variable. We multiply both sides by R2. Therefore, this become 1, here become R2. But this represent the derivative here, okay? Therefore, you can, what you can mention here, you can multiply, it's not multiplication here, is the question here is take the derivative, you can mention dr here and r t2 dr, okay? It's the same in meaning. Therefore, we are taking this term represent the derivative of this term here, okay, respect to r.
Okay.
And therefore, here we end up next term. Therefore, it shows the C1 is equal 0. And now your equation here, because you have R squared here, you have R to power 3 here, you can simplify the equation become like this, okay? And now you take, again, the question asks you to calculate the temperature as a function of R. Therefore, we take another integral from both sides, and the expression become here. This is integral become this, again, this become 1 over R2, and here is become C because you have the term is 0 here. This represents the derivative of constant 0. But now you have another boundary condition mentioned at R equal R0. It mentioned there is a temperature 80 degrees. And we can place this one here, and you can calculate this one. Okay, therefore you have it R equal mentioned 4 centimeter. I forgot what is the mentioned how much heat generation. It mentioned conductivity of the material. You have all this number. It mentions 80 degree. Therefore, from there you can place here, and from you can get this value that represent this one. Okay, Therefore, C2 become this value. You have the temperature 80, you mention heat generation, and so on, so on, so on. You place it here, and you can calculate this number. Okay. And for now, you have an expression, knowing amount of the heat generation, knowing the radius of the sphere, knowing conductivity and temperature, you can calculate the temperature at every point. Look at the difference between you're using finite difference. Here, you can change the R at any point from 0 to 1 millimeter, 2 millimeter, 5 millimeter, and so on, and to calculate the temperature at any point within the sphere. But when we are using numerical, since you have to slice it, discretize it, you find the temperature at a certain point. But this expression gives you the temperature at any point throughout from 0 to the radius of the block. That's the difference between when you're solving differential equation and when you're using numerical. But as mentioned, that we can do it this one because this problem is well defined. Any question, please? Any question? Then we go to next step at R equals 0. Therefore, you find the temperature here as equal to 791 degrees. Because we have the 80 degrees, we know the value of the heat generation, we know how much is the conductivity. Therefore, they put it down here, and you find the temperature at the center of the sphere is 791 degrees, while the outside temperature is 80 degrees. Did you have any quiz last week?
Yeah.
How disaster was? Okay, let me
get the results.
Pardon me?
We will see when we get the results.
Oh, you do not know. But what is your guess?
I think it's okay.
Okay. Very good.
Sir?
Yes, sir.
Maybe you can ask the TAs to do more difficult examples through the tutorials.
Good. Therefore, I will select the question and give it to her.
All right. Thank you.
You want to be challenging?
No. I'm saying not for the quiz, but I'm saying in the tutorial. When we practice. Yes.
The tutorial, as I mentioned here, is we give a number of the problems assignment, and also we identify some problem as for tutorial.
Okay.
Again,
I saw that in the
course outline.
The outline, yes.
Yeah. But the idea of tutorial is not the question difficult or easy. The question be able to have some discussion, that we go through the procedure and say why we use this technique, why that. That's mainly for the discussion. But if you would like, we can select other problem. I have no problem. But the idea here is it creates some environment that you can ask any question that you would like. Okay.
Okay.
But no problem. I can do that. We can ask to that. Okay, let's go to next problem. Again, I'm trying to go slowly because I know you are a little bit behind. Let's do this problem from chapter 3.
Before that, Professor, excuse me, can you go back to the previous slide?
This one?
Yes.
Okay.
That's it. Thank you.
No problem. Therefore, you have the solution to assignment 1, 2, and by default, by mistake, I send you also the 4. Okay. Therefore, you have the solution to all the assignment. Please do not look at the solution. Please do not. Try to do it and then look at the solution, because find out if you can do it or not and where you're making mistake. Okay. That's the idea. Now, we're getting close to the winter, right? Okay, to defrost ice accumulated on the other surface of your warm is blown over the inner surface of the shell. Okay, therefore that's the practical problem that we have. We assume is the window, the glass 5 millimeter and thermal conductivity is 1.4. The outside temperature is -10. And the convective heat transfer coefficient is 200 because you're going too fast, my friend. while the ambient temperature inside is 25. Therefore, you have the glass outside exposed to environment is minus 10 degree and convective heat transfer 200 degree. And inside, you have a convective heat transfer, is the conductivity is 1.4 for the glass and the temperature is 25. Now you're working for Ford or Chevrolet. You would like to design a fan to make sure the ice is melting down. What should be the airflow? Determine the value of convective heat transfer coefficient for warm air blowing over this interior surface. Therefore, you're trying to design a fan to melt down that ice. What should be the heat transfer coefficient? Therefore, you have a glass outside is minus 10. The convective heat transfer coefficient is 200 watt per square meter. And inside, the temperature inside the car is 25 degree. The glass is 1.45 millimeter and 1.4 conductivity. What is the convective heat transfer inside?
Sir, I have a question.
Yes, sir.
Do we assume that the ice is not there and we just want a temperature that goes above zero
That's right.
on the outer surface of the windshield?
Yeah, defrost, it means zero. Yeah. Anyway, I don't know if you're looking for co-op, and that's the Ford company is looking for a good engineer. How we are going to solve the problem? For dry glass, inside temperature is 25, outside temperature is minus 10 degrees. And draw also your resistance. You have resistance to the convective heat transfer outside, resistance to the glass, and resistance from interior glass to the room air. You know the convective heat transfer outside, therefore you know the resistance. You know the thickness of the glass, and you know conductivity, therefore you know the resistance to the glass. The only thing unknown here is resistance to inside, okay? Therefore, this is the problem that you did in building science. You're trying to calculate the convective heat transfer inside the car. That's exactly what's happening. You have minus 10 degree outside air, 200 heat transfer coefficient, conductivity is given, the thickness is given. The question here, what should be the resistance here, or convective heat transfer coefficient here, minus 25. And mentioned defrost, it means the minimum temperature you would like is 0. Therefore, that's exactly building science, my friend. We assume steady state. For the amount of the heat go from inside to the glass, pass through here. You know the convective heat transfer here, you know the temperature here, and you know the temperature here. Therefore, you know how much heat has been passed here, exchanged here. This amount of the heat transfer has to be exactly the same as heat transfer here. Okay? Therefore, we can solve this one here. This is convective inside, convective outside, and this is this one. Okay? Therefore, here we have for inside, here is for outside, and here through the window glass. Even you do not need this one because the amount of the heat from here to here is exactly the same as from here to here. Again, therefore you can write this equation that you have. The temperature outside that you have here, the infinity outside, minus T1 here, divided by resistance is equal from here to here. Or you come from here to here, it doesn't matter, okay? Therefore, from here, the only thing unknown that you have here is the value of Ri. Ri, we calculated, and this, okay? So this is exactly what you did it for in building science. So just considering here is a steady state scenario. The amount of the heat goes from here to here is the same as from here to here and from here to here, okay? Therefore, this is exactly, you have a number of resistance in series, the amount of the flow is the same, okay? The voltage from here to here is different, voltage from here to here is different, but the amount of the Q is, I is passing is the same. Exactly the same one we wrote it here, okay? We wrote from here to here is exactly from here to here. And here to here is represented by this step. T1 minus Ti here. Ambient temperature. And summation of two resistance from here. One from here and one from here. Any question, please? Any question, please? You finish?
Yeah.
Okay, good. Therefore, we go to the next slide. And from here, we calculate the same equation and find the convective heat transfer inside has to be 112. Okay. This equation that you see is come from the previous that we have Ri, this is Ro, and here is R, this one. Okay. Therefore, you have all those numbers. You know the temperature inside, you know the temperature outside, you know the temperature supposed to be minimum 0. Therefore, all the information is given. If you substitute here, you can find that the convective heat transfer inside is 112 watt per square meter. And now you can see, as I mentioned, air is a very lousy heat transfer medium. Therefore, you have to have a high speed in order to create that much heat transfer coefficient, okay? Any other question, please? Any question, please? Please go back and forth, chapter 2, 3, 4, and familiarize yourself with all the subject, okay? You should not have any problem chapter 2 because it's exactly as we did in building science, okay? Done?
Yes.
Okay, good. Therefore, now we go start to lecture again. You solve the problem one-dimensional, okay? Steady state, okay? The problem you did it in building science, the project you did it for project number 1, it was one-dimensional. We were trying to look at the heat transfer to the wall. But sometimes they give you a plate. The plate is two-dimensional, X and Y, okay? X and Y. And they would like to look at the temperature distribution inside this plate, okay? This is a simple scenario. Therefore, now we have to discretize the system in two-dimensional. We did it in X direction, here node, interior node, this exterior node, but also now we have two-dimensional. We can do it also in this direction, okay? The procedure is the same, exactly the same. Therefore, you mentioned that here you would like to have M node, for example, could be 5 centimeter. and here you need n node. Okay, this is the way you discretize. This could be 5, this could be 6, could be 10, this could be 20. Okay, therefore each node here is represented by two notation: m representing x direction and n representing y direction. Therefore here is the temperature at node mn. Okay, therefore here is mn, and here is m minus 1, and so on. Okay, therefore here is become m minus 1, here is become m plus 1. Therefore here represent this one, and here is down, here is n minus 1, and here is n plus 1. Therefore the temperature here that you have inside the material, this is solid material, therefore you have a conduction. Therefore this node exchange conduction with node m plus 1, conduction m minus 1, conduction n minus 1, conduction m plus 1. Therefore you write the same way we did it for one dimension, now you write it for two dimensional. Therefore we will simply write conduction from here to here, conduction from here to here, conduction through here and here. Therefore that's the way we write the equation to do that. Okay, therefore if I magnify the case that we have done here, as I mentioned, remember that here we do not, here is again the magic word. The magic word here is mentioned steady state. Okay, steady state. Okay, therefore here is no transient. We may have heat generation, but there is no variation of temperature as a function of time. Therefore look at here, I can write the equation here, and I mentioned rate of conduction, left, top and bottom, and so on. Okay, therefore these are the conduction come from this part, this part, this part, and this part. The rate of conduction coming to this node plus how much has been generated inside this node is equal rate of the change of conduction. But here we assume this term is equal 0. This term equals 0. Again, the same thing we did for a steady state. When you have a node here, the distance between this node and this node is equal delta x. From this node to this node, delta x. And here is delta y, and here is delta y. Therefore, we have to specify the mass associated with that node. Therefore, here again we write, here is the distance delta x. I draw the boundary here is x over 2. Here is delta x over 2, delta y over 2. Therefore, the dimension from here to here is delta x, delta y. From here is to delta x, delta y, and so on. Okay. Therefore, keep in mind here, please try to visualize the conduction from here, m plus 1 to here is through this surface area. Okay. Therefore, the surface area that you have is delta y, and the z direction is L. Okay. Conduction from here to here, the distance from here to here is delta x, is k over delta x times a. A is equal delta y times L. The conduction comes from this point, m, n minus 1 to m and n. Here is conduction. The distance between this node and this node is delta y. Therefore, become k over delta y, the distance, and the area is perpendicular to this one. Therefore, it is delta x times L. Okay, L, it means the third dimension. Okay, therefore keep track of this surface area and the distance. Okay, conduction comes from m minus 1 to here is, from here is k over delta x. The distance is delta x times area. Area is delta y times L, the other size, and so on. Okay, therefore keep track of the distance for conduction and area. Therefore here we write k from m minus 1, here is delta y, because the other length we assume is equal 1, okay? Divided by delta x, the distance from here to delta x. N plus 1 to here, okay? Therefore we are considering from here to here, from here to here. The distance from this one and this one is delta y, and the surface area is delta x times L. The same thing here and so on. Therefore, this represents conduction from left. This represents conduction from the top. This represents conduction from the right here. and here represent conduction from the bottom here, okay? Therefore, we wrote summation of the conduction to that point, plus how much energy has been generated. Again, in energy generated here is, this is per unit volume, okay? But what is the size of the system is delta X times delta Y and times L. Therefore, this represents one here, okay? Therefore, here you can see all of them, we ignore the L. Here there's multiply L, 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 L. And that's the third dimension, okay? Therefore, now, again, we go in, trying to write it in the nice format. Therefore, here is, we have 1 delta X squared, delta S squared, and so on, okay? The reason delta X squared here is we divide all the equation by delta X over delta Y, okay? In delta X, but delta X disappear here, becomes delta Y squared again, okay? That's why we have this square here, and so on, okay? Therefore, now we develop a procedure again to be able to calculate the temperature distribution inside the plate, okay? We're going to solve one problem next lecture that you can see it, because the most important part here is you have to keep track of the size of your control volume and also the location, okay? For example, if you look at here, if I assume this side is dealing convective heat transfer, and here is Q constant heat flux, therefore we have to keep track here when I draw a control volume here, I have to keep track of the conduction component, convection component, and so on, okay? I believe we have almost 4 o'clock. Do you have any question from me? I tried to ask this gentleman to provide you the report from the first part as soon as possible. But again, you can start to do your computer code as soon as possible. This will take some time, and I do not want to hear or receive any excuse email the last 2 days of the project. If you plan to become sick, please become sick now. If you plan to do something else to do it, please do not come with an excuse, okay? Any day late, 10% you lose it. Again, I'm available, the TA are available to help you to write this code as soon as possible. Again, this needs some planning and exercise to make sure that you're doing correctly, okay? Any other question, please? The lecture is finished. I'm here. If you have any question, I will be here for the next 10 minutes, please. Have a nice evening.
Thank you, sir. Have a good afternoon.
You too.
So it's a quick question about the project.
Yes, sir.
Of course, it has to be a computer program, but does it have to be MATLAB, or can it be a different program?
Any code that you feel comfortable, sir.
Okay. Another question: what if it would be sort of an Excel sheet where it's not programming, but there still are, you use the functions?
Well, I'm not really that much familiar with that thing, because here is you have to also move through the time. I do not know if Excel has done it or can do that one, okay? Because in the first project, yes, you were able to do the Excel because you were just inverting a matrix and multiply and so on. That's no problem. But the second part, you have a move through the time, and I have no idea how that can be done in Excel. I know MATLAB is easy to do it. I know C++ and so on, that can be, Fortran, that easy can be done, but I'm not familiar with Excel. Because you have to track also through the time. You calculate 1 o'clock, and then you move the next time step at 2 o'clock. But you need the information you calculated time equal 1. That's why I mentioned at the end that you have to keep the record of the previous temperature, okay? Okay, here, when before you go to next time here, when you finish time number 1, you have the temperature at 1 o'clock. But before you move to the next time equal 2, you have to save all of those previous temperature in your program, okay?
Right.
And then you go to time equal 2. And then you calculate the time over 2 because you need the temperature at the time equal 1, okay? When you finish time at time equal 2, you have to keep all the temperature from node number 1 to node number n, all the temperature, save them, because when you go to time equal t equal 3, you need the temperature 2. Therefore, this is, I do not know how to do it in the Excel, okay? And if it can be done, it's become very complicated and so on.
Right.
But you need MATLAB in your life, my friend. If you'd like to get a good, well-paid job, you should know MATLAB.
That's very true. Thank you.
No problem. And if you need to, probably TA, they can give you 5 minutes lecture to do it.
Right. Sounds good.
No problem. Any other question, ladies and gentlemen?
Yes, sir. I have a question for you.
Only for me, yes. What can
Okay, so for the program, would it be possible to, I guess, have an initial guess value for the future value and then find the initial one and then from there update it?
No, it doesn't work because the question here is whatever number you start, it doesn't work because you can guess. I mean, you can because it's transient, and the transient, it means the temperature changes function of time. You will see it in your result. Okay, therefore the temperature node 1, node 2, node 3, all of them will not end up the same time max. Okay, in a steady state, when you did it, all the temperature maximum was almost at the same time. Okay, because we assume whatever received here is immediately passed. But here is with some of the energy we store here, and the problem move to here next hours, and from part of the next from. Therefore, the temperature you have, whatever guess you mentioned, it doesn't solve. Assume any number. Assume is a hell in 1 million degree. That's we call it the initial value, and the effective initial value after a few hours disappear. Okay. Therefore, don't worry. Whatever assumption you make, initial value is initial value, and the effect is disappear after few hours.
Okay, I get that, but would it be possible to have like to guess an initial, like instead to guess the initial value, can we guess the future value and then from there get the initial value and update it like that? Or that's not mathematically
How can you
correct?
calculate the future value from future value to time that one? Because you do not know the future value.
Yeah, can you go like the next slide? Yeah, from here. Like instead of putting the, or is it the next slide? I think it's the next slide.
Because your future value is dependent on the time now.
Yeah, but can we do it like the reversed way? I don't know. It might be mathematically incorrect, but
Mathematically is correct, but even if you would like to solve it inverse technique, they call it inverse. You do not know the time temperature here. You do not know this one. You do not know this temperature here. You do not know any of them. Inverse,
but what if you
inverse
put in
inverse indicates if I, for example, if I have a sensor and I place at the temperature sensor, I measure this temperature, then I can solve it inversely, calculate what was the temperature 10 minutes ago. But now, with a practical way, if you look at here, I have a sensor put in the wall. I measure the temperature in my wall here is this. If you look at the practical way, what would be the temperature next hour? Therefore, you know the temperature now, and you will calculate the future, okay? But since you do not know any sensor, we call it initial value. You can assume any number, and it doesn't matter. Why are you wasting your time to calculate this sum? Any number. And that's why about the partial differential equation, you have a boundary condition, but also you have initial value. And this initial, we call it, the name is initial.
Right.
And the effect disappear fast.
Right. Okay.
You
Thank
don't
you.
need to do that, okay?
Yeah.
Whatever, just for curiosity, put this one, any number, and you will see after 3 hours, the effect disappear.
Okay.
No problem.
Okay, thank you.
Sure then. Any other question there?
Sure. I see what you're saying. The initial condition doesn't matter after 2-3 hours, but why is that the case? Why is the initial temperature doesn't matter?
That's exactly the differential equation, my friend. Differential equation, you need a boundary condition and some initial value started. Therefore,
Okay.
this is initial value. The effect is, when I start to simulate, you will see the effect probably for the next 3 or 4 hours. This number will affect, for example, until 5 o'clock, 6 o'clock will affect. But after that, those effects disappear, and then the effect of the outdoor temperature and so on will affect, okay? That's why here we have the differential equation. That's why we mention partial differential equation, boundary condition and some initial value. And most of the time, in most of the problem, we do not have the value, because I'm trying to find, if I want to design a building, I do not know the temperature of the wall, because the building has been there for some time. Therefore, I do not know. What I do, I guess some value and solve it through here, this technique. And I said, now, okay, I can run this program for the winter and trying to look at the whole winter, what would be the temperature variation on the wall, okay? Whatever it was initial, disappear.
Okay, okay. Yeah, okay.
And that's, again, for curiosity, when your program is working, just change this initial value and you will see it. You will see this effect. And this is exactly the whole idea, that you have some understanding of this differential equation. You see this differential equation day and night, but it doesn't make sense to you because this is only differential equation. But when you try to solve it, and you will see the effect, how it's, okay, let me go back here. Okay, this differential equation that you have here for you is only a differential equation, okay? How it works, you have no sense, okay? You have no sense of what that means. But when you look at the solution, you will see this effect. And that's, we call it thermal lag. You can see, for example, solar radiation, the maximum, for example, in South Wall, it was at 12 o'clock in noon, but the maximum temperature will show 3 o'clock in the afternoon.
Yes, yes.
And that's exactly, we had in building science. Remember cooling load factor?
Yes.
Remember, my friend?
Yeah.
Did you pass that course?
I think that's why I'm here.
No, I'm joking, my friend. The cooling load factor, and that's exactly happened here. Because this maximum solar radiation is at 10 o'clock, but the effect on the room temperature, it appeared at 2 o'clock in the afternoon. That's we call it the time lag.
Okay, yeah, I see the idea.
Good.
Sir, I do have a question from the assignment questions. In one question, I get the Fourier's number lower than 0.2.
Yes.
The solution still tells me that I need to solve it by assuming it's one term.
I mean, I do not remember the number, but if you tell me what problem it was, I can check and let you know. Because
yes.
if it's less than 0.2, therefore you can use the figure.
Yes.
Okay.
Yeah, that's what we do. The solution tells me to do this.
Okay. Again, I have no idea which problem it is, therefore I cannot answer you right away. But if you tell me, I can go back and check the problem and I give you an answer. But
could you go to the? I'm looking at the chapter 4 solution.
No, I do not. Again, let me just go back. Rather than answering a specific problem, let me go back and show you the lecture server. Okay, look at here. The case we had this part, right? This one here, right here. Okay. We mentioned if the case is like this. Okay, this was the equation that we had. This is the general solution, no restriction. We mentioned if it's more than 0.2, we use simplify equation that you have here, okay? And for this is for the case if Fourier number is more than 0.2, okay? But if case is not, you can use this graph, okay? This graph solution apply for anyone, okay? Therefore, or if you don't like the graph, you can go back and use this one. But this one is very complicated because you need the eigenvalue number and so on. And therefore, somebody plotted this one for you. And that's the plot, the graph, you see it? This is the graph here. This is the solution to that problem, to that equation.
Oh yeah, that's where we have to go to the table to find the eigenvalue and A.
That's right. If that only case, that the table 4.2 or 4.3 is for the case is applicable is when the Fourier number is more than 0.2. And that table 2 and table 4.2, 4.3, they gave you the eigenvalue and the answer to the Bessel number that you have here. Okay, these are the numbers that you have.
Okay, sir. But in this case, the Fourier number is lower than 0.2.
How low is this?
Is 0.1217.
0.1.27. Okay, again, this is again, the person solved the problem if he was lazy. But you can go back and then make sure you can use this graph. You have this graph, give you the temperature at the mid-plane, at the center of the wall. And if you need the temperature to look at the other point, you can use this graph here, okay? Therefore, the figure is, again, is much easier to use as an engineer, but those that one term equation that's given to you is only for the case is the Fourier number is more than 0.2. But probably the solution here, again, they're making some assumption.
Okay.
No problem, sir.
Yeah, thank you. But I'm saying, you just said we use the table when the Fourier number is smaller than 0.2?
No, sir.
A bigger one?
No, sir. When I mentioned if you would like to use this equation, look at here. This equation is only the first term, lambda 1 here, and Bessel function that you have here, okay? In order to do that, you need to know the value of eigenvalue, lambda 1.
Yes.
And that's the table 4.2 and 4.3 is only applicable when is this term for this one. The eigenvalue that given on the table is for the case the Fourier number is more than 0.2. When it's 0.2, you can use only the first term. If you look at this equation, is the same as this one, my friend, but only selected the first term. And when they select the first term, that's been simplified to this one. And if you use this equation, as I mentioned, error is less than 2%.
Okay.
And here is specify again, this is only applicable when the Fourier number is more than 0.2, Fourier number is 0.2, Fourier number is 0.2. This is the only time that you can use it, okay?
Okay. So do we use the for equation when Fourier number is lower than 0.2?
Then you have to sit down and do a lot of work, my friend, because the question here you can see is from 1 to infinity. Therefore, you have to solve those one to find out what's the eigenvalue, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, and on. And that's the case. Rather than you do it, somebody has done it and came out with this graph. Therefore, you do not need to solve it. You can come and use this figure that you have here.
Okay.
That this figure is the solution to this equation.
Okay.
This solution to this equation for any scenario, for a number less than 0.1 or more than 0.1, and is given by this graph here.
Perfect.
You can see here is the Fourier number is going from 0 to infinity, 700 and so on, okay?
Perfect. Thank you so much.
No problem, sir. Any other question?